everyone, and welcome to today's webinar, Discover the Power of Tubular Ultrafiltration in Direct Filtration Applications. So, well, first of all, thank you for joining us. I would also like to give a special thanks to our speakers, who are the real stars of today's session. Just a quick introduction. My name is Elena Meave. I am the manager of the Knowledge Center at Berghoff Membranes, and today I will be moderating this webinar and introducing the topic of tubular ultrafiltration in direct filtration applications. Before we begin, just a couple of reminders. First, just let you know that this webinar will be recorded and that the presentations will be shared with all of you afterwards. And secondly, we strongly encourage you to ask questions. So for this, you can use the Q&A button in this Teams event, most likely located at the top of your screen. So, well, feel free to submit your questions at any time during the presentations, and we will address all the questions in the final part of this webinar. Then, why we decided to organize this webinar? Well, first of all, we intend to raise awareness around the key drivers and growth opportunities for tubular ultrafiltration in industrial applications. This is why we have been hosting webinars like this for several years, and we are very proud of the results. Thinking on wastewater management, let's say, the imperatives for reuse, recovery, and waste minimization are today stronger than ever. And well, moreover, UF is now the technology of choice for separation or fractionation processes in several industries such as biotech, food, chemical, and many others. And tubular ultrafiltration stands out as a cost-effective, efficient, and high-performance solution for this. Then, what are our main goals today? Well, first, present tubular UF technology for treatment, separation, concentration, and recovery processes through the expertise of some of our OEM partners. We also want to create networking opportunities among the key industry players and, of course, increase awareness and educate on tubular UF technology and its huge potential for industrial applications. So now let's explore the potential applications of direct tubular ultrafiltration. First, we have wastewater treatment and reuse. Some examples can be oily wastewater treatment or CMP wastewater from the microelectronics industry, for example. Secondly, we have the waste management group, meaning that tubular ultrafiltration is used for reducing the volume of waste to be managed externally, or, for example, when evaporation is applied, the energy costs are greatly reduced. We can also apply tubular ultrafiltration for effluent policing after existing treatments. And finally, we have the recovery of valuable products group, where normally it is the reject or the concentrate the desired product. Okay. So moving on the next slide, when talking about external cross-flow filtration with tubular membranes, we can highlight some benefits associated to this technology. Due to the membrane configuration and the mode of operation, there is a superior fouling resistance, which allows to deal with the most complex industrial wastewaters and process streams. These membranes can deal with high suspended solid concentration, high oil and grease, and organic matter concentration, and still deliver high permeate fluxes. As you may know, maintenance and inspection is quick and easy, And finally, these are plug-and-play systems with minimum footprint requirements. In the right part of the slide, you can see some key parameters, okay, applied in direct filtration systems. You can find the recovery or alternatively the reject that needs to be set in a way that the project is as cost effective as possible. And then in terms of global operation, we can also find different operation modes as the batch or semi-batch process versus the continuous or semi-continuous reject operation mode. So nice. Well, considering the drivers and opportunities presented in the previous slides, we as Berghoff Membranes decided to host this webinar together with our partners, Bafilin, Sepra, and Dynatech Systems. They are, of course, top experts who will disclose their expertise, experience, will present their real case studies dealing with direct filtration applications of tubular ultrafiltration. So now, having said this, I will proceed now with a very brief introduction of Berghoff Membranes as the host of this webinar. Well, as you may know, Berghoff Membranes is a German manufacturer of tubular ultrafiltration membranes. We are part of Berghoff Group as one of its 6 business units. Our tubular membranes are mainly advantageous for industrial applications in general. We have references across nearly all the industrial sectors worldwide, including food and beverage, landfill leachate, biogas plants, chemical industry, and many others. And well, with over 50 years of experience, we have successfully delivered more than 2,500 projects globally. Today, we operate from 4 locations. We have the headquarters and production facility in Germany, the trade office and application center in the Netherlands, and additional offices in Spain and Singapore. And well, in terms of general applications, we focused on MBR, anaerobic MBR, and direct filtration applications, which is the topic for today's webinar. Here you can see how our tubular modules look like. We offer membranes with different geometries, pore sizes, materials, including both backwashable or non-backwashable options. Additionally, we have a special chemically resistant membrane, which is designed for projects where ultrafiltration is combined with chemical precipitation processes, such as brine recovery, softening, or heavy metals removal. And for the housing, we also provide various materials and dimensions to suit well, different applications, capacities, and select the optimum design for each specific project. Okay, so now, well, we have completed the introduction. It's time to move to the to the expert presentations. So for the first session, I am pleased to welcome Jos van Dalfsen, Managing Director of Bafilin Systems in the Netherlands. Bafilin specializes in advanced membrane filtration with a strong focus on developing sustainable membrane processes that help customers recover valuable ingredients, save energy in downstream processing, and enable water reuse. Under Jo's leadership, Bafilin System continues to drive innovation in the food, dairy, and beverage industries. So, well, Jos, the floor is yours. Please share your screen and begin with your presentation. Thanks in advance.
Thank you, Elena, for introducing me. Couldn't do it any better. Let me share my screen in the meantime. So yes, good afternoon, and thank you again for introducing me, Elena. My name is Jos van Dalfsen, and today I'm going to present you our philosophy and applications in direct filtration using tubular UF, specifically focus on the Berghoff membranes, of course, applied in the food and beverage industry. Let me introduce you shortly our company before we dive into the matter and the topic of today. Well, you already introduced me, so I will not repeat that anymore. That's a bit too much, I would say. But a bit about the company. We are a OEM specialized in membrane filtration, based in the Netherlands. Our office is not that far away from the Berghoff office. Actually, we are located in the same city, and that's why we have a good and close cooperation with Berghoff for many years. But I do have to say and have to highlight that we are an independent membrane application specialist, meaning that we offer a variety of membrane designs and membrane cutoffs to our customers based on the application that we are dealing with. And sometimes it's a Berghoff membrane, and that's of course the majority of the topic of today. But sometimes there are alternatives simply because the process or the process conditions requires that. But I will touch on that a bit later. Like I said, we are specialized in membrane filtration. We design, deliver, and integrate full-scale systems in the food and dairy and beverage industry. And mainly, these are hygienic design systems because of the industry that we are targeting. Nowadays, we are with about 25 employees here in the Netherlands, and they are all in the company serving as membrane specialist. Our coverage or region that we focus on, like I said, the markets is highlighted in this slide, and the regions that we are targeting. We started in the Netherlands as that is our home base. Nowadays, we're quite active in the UK and in Ireland, and let's say Western Europe, so Germany, Poland, south part of the Netherlands is our market or region that we are targeting. The way we work is maybe similar to the people that are currently in the audience, maybe not, but how we often start, especially in new applications where membranes are relatively unknown to the customer, we have to test and select the right membrane for that application. And I will show an example after this slide as well. But we have in-house application facilities, so pilot facilities, testing facilities. We have our own mobile pilot units, which we use to test, select, and validate a filtration process for our customers. And with that data, after the validation, we use that data to design a full-scale system. So we have process engineers, mechanical engineers in-house that do the process design and mechanical design up to the working drawings. And we outsource the manufacturing of skids, but we are in charge of integrating them, commissioning them on site with the customer, and are in charge of monitoring and service those systems after they've been installed and are up and running. So that covers a bit the services and activities that we do when we are uptaking a new project. And like I said, we are independent when it comes to our membrane know-how. So we don't produce our own membranes. We use, for instance, suppliers like Berghoff, and in a wide variety of cutoffs, depending on the purpose of the application. We focus on micro filtration. If it's on protein recovery, it's often ultrafiltration, of course. And if you're more into the multivalent ions or sugars, then nanofiltration is in place, and our role often to recover water for in-process recovery applications. And that's also why we have a wide variety of types of membranes in our portfolio. Elena already, of course, introduced the Berghoff portfolio, which is a type of membrane that we often use as well. But besides that, if process conditions in temperatures are becoming higher or pH variations are more extreme, then ceramics are sometimes the preferred choice. And spiral-wound membranes are often in place also in dairy applications. And those are different elements and types of membranes and configurations that we pre-select before we are screening and validating a process. Because the industry that we are targeting is the food, beverage, and dairy industry, and we are dealing with a lot of different feed streams. So it can be protein hydrolysate, so typically high temperature products that you see in the left picture, 80, 90 degrees Celsius, and there we have to clarify the stream and remove fat residues in this product to get a clarified hydrolysate. That's on the right bottom bottle in this picture. And there we often choose to select a ceramic membrane. On the right picture, you see a seaweed extract, higher turbidity. So spiral wounds are not a choice of membrane there. This is typically done with a Berghoff membrane in this case as well. So we look at the feed composition, the process conditions, and of course put that next to the membrane limitations that we are dealing with from different manufacturers and suppliers. So that's how we, let's say, select the right membrane per application. Now, if we focus a little bit on an example and a case that we have been developing a couple of years ago for one of our customers here in the Netherlands, which is focusing on recovery of water and proteins in a potato starch factory or process. This is an up and running process, and recovering starch from potatoes has been done for many years, of course. But the focus on protein recovery and water reuse became more active over the last decade. And we were connected with this customer in the Netherlands, and they asked us, can we optimize our existing process? Can we integrate a filtration solution in a brownfield situation, so in an existing factory, knowing that we are dealing with quite a challenging feed stream? And the purpose was to reduce energy consumption in the existing process, especially in the coagulation and evaporation process, reclaim water from the potato, and preferably increase the yield of protein recovery in the coagulation process as well. So what we are dealing with is a crop, a potato in this case, and the main product for this factory is to reclaim or recover the starch from the potato, which is about 18% of the total composition of a potato. And then what you have left is a bit of residue of fibers, of course, fat, proteins, and a lot of water, which is part of the potato, of course. So the existing process is relatively, well, in a simple scheme is like this. The main purpose main target of this customer was to reclaim and produce starch and fibers after rasping and grinding the potato. But what you have left is a fruit water, we call it potato fruit juice or fruit water, that is further treated in their process by a steam coagulation process. Then the proteins are being coagulated and separated and then dried. So this is their existing process, how they've been doing that for many years, many decades in time. This is not our focus, so starch and fibers are already being separated, but we are dealing with a fruit water coming from the potato. And like I said, so the existing process of extracting and treating the potato juice is like this. So the potato juice is going to a defoaming tank. Capacity is relatively large. Also, it's about 240 cubes of potato fruit juice per hour. And that total volume is sent to a coagulation process where they inject steam to coagulate the proteins. Then the proteins are being separated by a decanter. And the residue is sent to evaporator. Evaporator needs electricity, of course, to extract the residue products that are still present in this potato juice. So large volumes, high energy consuming process that they have been running for many years. So the aim of the application and trials that we were asked for is to design on paper first a direct filtration process without integrating additional pre-filtration or separation processes like decanters or separators, because the volumes are simply too large, and it would become less cost effective if we have to build up a complete process line just to treat the potato fruit juice. So when we were selecting the membrane for this application, we knew that we are dealing with a feed stream with a high solid load, fibers present in the fruit juice that we have to deal with. So we selected tubular membranes for this application for protein concentration, but also knowing that the residue of fibers is still present. So we built a containerized unit together with Berghoff, selected the membranes for the trials, 8 millimeter membranes, and we did multiple runs for multiple campaigns, so over a period of a couple of years, because the crop variations do variate over time. One year the protein yield or the potato composition can be different from the year after, depending on the season fluctuations. Also, trials with variation of potato species have an effect on the potato juice composition. And of course, we're dealing with a industrial situation where foam becomes present when you're adding air or integrate air in a process. Foam, especially on potato juice, might appear very rapidly. So we have to test, find a suitable defoaming agent that is also compatible with the membrane that we selected. And we tested and validated a complete line of CRP protocols to clean the UF membranes, but also the RO membranes that are in place. But today I'm talking a bit more about the UF, because was also the most challenging part of the complete filtration process. And like I said, we don't add a pre-separation or decanter process in this process because we want to have a direct filtration opportunity. But then you have to, then you face the fact you're dealing with fibers in the potato fruit juice. And you see that on the left picture, accumulated material is forming on the head of the membrane. Even though we're dealing with 8 millimeter channels, we still see a growth of fiber layers on top of the membrane. So what we did is we integrated and tested a counterflow current over the membrane. So we alternate the flow direction over the membranes. So once you get an accumulation of fibers on the top of the membrane and you change the flow over the membrane towards the other direction, you basically loosen up the fiber material on that side of the membrane and can continue the process without cleaning the membranes frequently. And we changed the variations and the period of counterflow. We tried to optimize that in this pilot phase, but that also enabled us to design a stable process. And nowadays the units are running, I think, for 36 hours without a CIP interval. So quite an optimized process. Maybe different CIP integration and also period than normally is done in MBR, but in food industries, the frequency of CIP is per definition a bit larger. So what is left is a UF permeate that you can see on the right picture as well. That is sent to the RO for the treatment and produce clean process water that they can reuse in the factory. So schematically, it's like this. So instead of sending the potato fruit juice directly to the coagulation line, we add a concentration step. So we concentrate the proteins and the fibers as well, because that's all collected in the same product, and that is sent to the coagulation. And then the UF permeate is sent to an RO where we produce reusable process water. So again, back to the original process. So what is then the result of this? So we integrate a UF and RO process in the existing process. So after the defoaming, we installed relaxation tanks and also defined the right defoaming agent, of course. And then the UF concentrates the feed stream with a factor of 3. And then the concentrate is sent to the coagulation line, which means that you need about 60% or 65% less steam for the coagulation, so which energy reduction in that part of the process. And also for the evaporator further downstream. And then the RO is receiving the rest of the UF permeate, also has its own concentration factor, and the RO permeate is sent back to the process for potato washing, for instance. So in this way, we produce and process about 240 cubes of potato fruit juice an hour over the length over a campaign of about 6-7 months. So because a potato campaign is not a full year in a row, but it's typically in the Netherlands about 6 to 7 months campaign period. So based on these trials and selection of membranes, we came up with a full-scale design. So in the end, we delivered a full-scale plant consisting basically of 6 UF skids that you can see on the left side of this image. 5 skids are always in production, and the 6th skid is in standby. So the 5 skids have enough capacity to treat 240 cubes an hour of potato fruit juice, and the 6th skid is in CIP mode or in standby mode. So we always alternate the frequency of CIP with one of the skids. So we always have a continuous process, and we don't have any downtime during CIP, which is important in these kind of processes. So in total, we have installed about 108 UF modules in this installation, and we are now running, I think, the 6th campaign because we commissioned the plant in 2019. In the meantime, we also delivered similar systems to one of their other factories in Germany as well, a bit smaller process. There we have installed 3 of these kits. So in a nutshell, what we enabled and what the customer received is a UF-RO system that enables the customer to increase the protein yield, because the concentration has a benefit for the coagulation process as well. Energy reduction in the existing process lines like coagulation and evaporation process. And of course, water reuse opportunities with integrating an RO system after the UF. And what we have further developed based on this application, that we also can integrate these kind of tubular UF processes in other biorefinery processes. So think of crops like sugar industry or pea processing industry, where you have a relatively high load of solids in the feed stream. That's where tubular UF can be of value as well. So not much to deal with wastewater, but a membrane coming from a wastewater application integrated in a food processes. And that's also a bit the take-home message and the experience that we have gathered over the years as well. Like I said, typically a membrane that's often used in MBR, for instance, or in wastewater application, has its value and purpose in upcoming industries where membranes were still relatively unknown towards these industries, but are a key factor in a successful integration in these kind of process conditions. And we also see that developments of membranes also within Berghoff allow us to have more choice and flexibility in selecting the right membrane for these applications. And in the Netherlands, we see a growing demand, even though we have a lot of surface water. The lack of water is becoming more and more an issue, and it's not longer a byproduct, or it's not longer a sustainability goal, but it's basically a license to operate. And that's where membranes play an important role in as well. And in the last case, I think that's key for us as well. Collaboration with membrane suppliers like Berghoff for this application, but also for other applications is key for us as well. And also, of course, with the end user, our customer in this case, allowed us to test and validate a system first in a containerized unit, but then also allow us to upscale from these pilot trials to a full-scale system, resulting in still one of our biggest projects in the Netherlands, and quite a good case to present our other customers as well, to convince them that membranes can be of value in these kind of applications. I think that's the last slide that I had. Feel free to ask any questions. I think later we have time for that as well. And for now, I would like to thank everybody for their attention, and looking forward to answering your questions later.
Okay, thank you very much, Jos. That was clear and interesting presentation. So yeah, at the end of the webinar, we will go through potential questions. Thanks a lot.
Thank you.
Okay, I'm going to share my screen. Okay, so next we will continue with the presentation by Giancarlo Tansi from SEPRA in Italy. Giancarlo holds a degree in chemical engineering, and after some years in chemical industry and an MBA master, he entered the membrane industry in 1993. Then in 2000, Giancarlo co-founded SEPRA, an engineering firm specialized in separation process engineering with a focus on membrane technology. Today, SEPRA has two facilities, the original site in Cesano Maderno, dedicated to membranes and accessories, pilot plants and applications development. A second factory is located in Montecchio, dedicated to the assembly of membrane skids. So, Giancarlo, let's hear from you now. Please share your screen and proceed with your presentation. Thanks in advance.
Okay. Thank you, Elena, for inviting at the webinar. Just confirm that I shared my screen correctly.
Not really now. What we see is like the second screen.
Okay, let's do like this. I know that when you're using two screens, it's a little bit tricky. Now it's okay.
Now you are not sharing the screen right now. You have to re-share, I think.
Let me on quickly. Screen number 1, that should work. Okay. What you see now?
You are not sharing the screen right now.
Not yet.
No. Eso estoy haciendo eso.
Now it's working.
Let me check. Yeah, but it is working the same way than before. So it is not like the full screen. I don't know if what we can do is notice I can share my screen and put your presentation.
Or we go on, because here it's always working like this.
There maybe you can use some of the buttons before to make a. Let me check.
Right, finally. This way it works.
Now it was working.
Okay. Okay, it's working.
Yes. Now we can
Good.
see your full screen. So
Yeah.
you can go to
Sorry.
the beginning. Don't worry now.
I apologize for.
No, these things many
Yeah.
times happen when sharing. So
Now it's not okay.
okay.
Okay, so again, apologize for. I will go quickly through the introduction because Elena already mentioned that we've been dealing with membranes for a long time, and both as a membrane supplier, cooperating with different partners. Berghoff is one for sure. We have been cooperating with Berghoff for a long time, but also supplying membrane packages. Having this wide view on the market, because we both work with OEMs, the contractors, engineering company, and with end user, we have a pretty wide view of the market, and so I will try to give you, after the previous presentation that was very interesting, focusing on a specific case, I will try to give a more general overview about different application for direct filtration, and then focus on a case that is interesting, particle removal, because it gives us an overview on different issues that are related to direct filtration. First, a quick note about what we intend for direct filtration in case for this cross-flow application. We refer to direct filtration when we talk about applications that are not related to biological treatment, either aerobic or anaerobic. Today, MBR application where tubular membrane are used in a cross-flow configuration together with aerobic treatment are well consolidated. I would say we see more and more anaerobic application for tubular membranes, where we try to refer to direct filtration, but it's not really direct filtration, because in this case, there is always a biological process in operation together with membranes. Today, I would say we try to focus on membrane application where there is no biological treatment. So we really do direct filtration on the raw wastewater or raw feed. And in this case, we see possibility to use different type of membranes, both 5 and 8 millimeter tubes in case of PVDF tubular membranes, because in some situation, the amount of suspended solids is not too much, like normally it happens in biological treatment. And so a smaller dimension channel may be interesting because of the higher membrane area per module. We have seen over years different cases of direct filtration application. And to start with, I would like just to mention a few cases we have been dealing with to clarify how different, how varied can be the application of tubular membranes in industrial application. Here, for example, I mentioned some cases that we've seen also recently, One is dairy wastewater. Dairy wastewater, normally one would expect that you deal with dairy wastewater with biological treatment, and this is still the more common approach. In the later years, we have seen more and more interest to treat directly dairy wastewater with filtration, and there are basically two reasons. One is the more compact design. In some situations, dairy factories are limited in floor space, and so biological treatment somehow is difficult to implement. And another driver we have seen is that more and more organic stuff, concentrated organic stuff, is evaluated for anaerobic treatment. The continuous growth of anaerobic digester installation increased the demand of raw material, organic raw material, and dairy wastewater is possibly one source of cheap waste raw material that can be used to produce biomethane. That's why direct filtration on dairy wastewater, above all on smaller dairy factories that are maybe located in urban areas, is becoming an attractive approach. Obviously, ultrafiltration itself is not enough. It must be helped by something else that typically is reverse osmosis downstream. But summing up, ultrafiltration to handle with bigger organic stuff, also some fat, grease, and solids, together with RO to trap the dissolved organic solids, generate concentrate that can be directed to biogas and biomethane production. Another case that we've seen that I would like to mention here is direct filtration really for solid particles. And recycled plastic industry has been a challenging example. More and more we are targeting reuse of waste, and plastic waste is one of, in terms of mass and volume, is one of the most important solid waste. This generated a big growth in platforms that are collecting and recycling plastic. One way to pre-treat plastic is to cut in small pieces, let's say, to make it simple, and then to clean in water and then separate by gravity in water. And this generates high amount of polluted water with residual plastic particles that should be recycled. We have seen, we did test and we have seen a real installation also for plastic residual solid plastic particle recovery in order to also reuse water in the same cleaning and handling installation. And another case that we have seen is cosmetic industry. Typically, waste stream in cosmetic industry that are contaminated by a significant amount of cream residuals. Residuals that are organic, okay, but they're not they're not really biodegradable, and they are not so, let's say, viable in the traditional biological plant treatment. What we've seen here is, for example, to separate and concentrate the water, like water that is used to clean equipment on the end of production lots, to separate selectively this water and to concentrate the high molecular weight or organic content, to concentrate it physically by simple filtration, and finally to concentrate up to a level where it can be handled almost as a solid waste into incinerators. Obviously, in this case, the challenge is to increase a lot the dry substance, and in a specific case, we have an installation that is shown also in this picture, where there is a pre-concentration with tubular membrane, and then there is also a final concentration stage made with inorganic membranes. We, as a company, we have cooperation with different suppliers, and so we happen to mix, even in the ultrafiltration range, different type of membranes in order to optimize the complete production cycle. Then mentioning some application in textile industry, where we have seen also some interesting but very specific cases for wastewater treatment. One is related to a wastewater application in a synthetic textile production line. I'm mentioning this not because of the let's say repeatability. This is a very special case, but because it was an opportunity to switch from the more standard membrane PVDF, loose UF, that is a standard in biological application. Here we have been forced to switch then to a tighter membrane, tighter PVDF, the 66.01 tight UF, because of stability, flow stability. Probably the fouling that we experienced in the standard membrane was related to the size of particles that tended to stick inside the pores of the membrane, inside the support. And this is a topic that may introduce also the following topic that I'm discussing. So, up to now, only very general considerations about how wide can be the application of UF tubular membranes, really considered as pure filter. And now I'm focusing on, let's say, I would say it's a special case, but it's not so special, because we are going really deep into the topic of pure particle filtration, where it's still cross flow, but the cross flow is purely working as a filter. There is not much in terms of organic stuff involved. There is no biological treatment. There are particles and there is a filter. And the topic that I'm approaching here is silica or silicon. It looks very special, but then when you look around, silica or silicon particles are spread all over many different industries. You find water silica dispersion, silica suspensions, because obviously here we're not talking about reactive silica that is soluble. We are talking about suspended silica or silicon. And it can be found in many different industries. I give you some examples, but I think these are not the only ones. Semiconductors, and in semiconductors is more silicon, while in ceramic and surface treatment, we mostly find silica, so silicon dioxide. In many cases, it's interesting to note that when we're talking about silica, we are talking about particles that are in a wide range of sizes and type. So we find both crystalline and amorphous particles, and we find particles that have a size range really wide, from the typical particles in the 10 micron range, 20 micron range, so small sand particles, down to the nanometer range. So we find basically colloidal particles that are in the 50 nanometer range and less, even less. It is possible to synthesize very small silica particles in the even smaller than the 15 nanometer range. This means that when we have this type of suspension, quite often the sedimentation time, even if we're talking with particles that theoretically should have a high density, in this case, sedimentation time may be very long, and it's impossible to achieve really separation concentration by simple gravity settling. When industry is dealing with this type of particles, normally we are talking about chemical physical treatment, normally used, high amount of chemicals, and because you need to use coagulant and polyelectrolyte to separate these particles. And then even if the chemical physical treatment is working fine, produced water is finally polluted by chemicals. And what happens is that then it is basically not reusable water. It's important, this aspect is very important because when we're talking about silica suspension, the water itself may be pretty clean. In case of semiconductor, is almost pure water. So removing the solids would mean that you are recovering not water, but really extra high quality water. Here, direct filtration comes with a very big advantage, that is that you are not adding chemical. It's a physical process, pure physical process. And we have seen applied direct filtration on silica suspension in these industries that I mentioned. So different type of industries with success, where the filtered water is completely clarified, because even selecting the molecular weight cutoff of the membrane itself, you can go and into separation of really submicron range particles. It's not contaminated by additives, and concentrate can be concentrated quite a lot. It means that in some cases, because of the increasing concentration, the particles begin to separate by gravity. Another interesting aspect that I want to mention is that in this direct filtration application, where the media itself, water, is pretty pure water, what happens is that when the filtration, the hydraulics are fine, and the porosity of the membrane is correct, the permeability of the membrane is really high. I mean, we have seen in this filtration application permeability quite high, somehow similar to pure water permeability. And these impact both on CAPEX and on OPEX, because the system is smaller, and also the energy consumption is less. Everything is fine. No, obviously challenges are there, because we are going into a demanding industry, and even direct filtration has some, let's say, critical aspect that should be considered. First, energy, obviously, because cross-flow, it's still cross-flow filtration. I mean, even if the water media is good quality, if you do not input energy in the process, what happens is that you will anyway quickly form a dynamic layer on the membrane, and the permeability will drop dramatically. So finally, you need to recirculate. We have seen that backwash may help in this application, but not backwash alone is not enough. And second, there are some hydraulic issues that are important that you normally don't see in other applications, and you see in this very special direct filtration application. One is abrasion. Normally, we as membrane people are not so worried about abrasion. And above all, when you're talking about PVDF tubular membrane in biological streams, it's quite difficult to have problem with abrasion. We have seen some cases, very extreme membrane bioreactor, where there maybe the prefiltration up front is not too good, but it's quite difficult to have abrasion because the suspended solid concentration may be very, very high, but we are always talking about flux, about bacteria, about inconsistent solids. While here we are talking about particles, and above all, if you're not separating up front the bigger and most solid particles, you may face serious abrasion problem. And second, the hydraulic behavior of the solution is quite strange. They tend to be similar to water low concentration, but quickly they will show a non-Newtonian behavior in terms of viscosity, pumping, and so on. So pumping system may be quite critical. Because of the type of pump and the type of mechanical seal that we are using. And again, normally in this tubular membrane application, we are not really worried about the membrane selection. A good quality centrifugal pump will do the job for MBR. Here, not really. Here you need to be cautious in how you select the pump. In terms of cleaning, it's in some cases you don't even need chemical cleaning simply because there is no real membrane fouling. It's, I mean, we're talking about water and particles. So some fouling may be related to very small particles going inside the pores, but in this case, you need to think about backwash, mechanical backwash, not really about chemical cleaning. And this is also somehow different from what we see in other situations. So I tried to give you a general picture of a very, let's say, wide and complex world. It was not, these 10 minutes that we have available were not intended to go into real details. But I think that this general review is important because we have been maybe too much focused in the past on biological processes, while in the next years, direct filtration physical process may become an important part of our activity. Elena, so I see time is expiring, so.
No, many thanks for the presentation, and yeah, I fully agree with you that sometimes we tend to not to think on direct filtration options, and there are possibly a lot of potential projects waiting for it. So well, many thanks, Giancarlo. see you later at the end of the webinar. Now I am going to
Okay.
share my screen again.
Thank you.
Thank you. Okay, so well, now, last but not least, we have Mike Butler, our next speaker. Mike is a sales engineer at Dynatech Systems in the United States. Mike holds a degree in mechanical engineering and an MBA from Drexel University. He brings extensive experience in delivering water treatment solutions to both municipalities and industrial customers across North America. Together with Dynatech Systems, Mike has deep experience in membrane technologies, including ultrafiltration, nanofiltration, RO, and MBRs. They have unique expertise with tubular UF systems applied across a wide range of industries, going from food and beverage to landfill leachate, as well as numerous recovery and reuse applications. Mike, over to you. Please share your screen and go on with your presentation. Many thanks in advance.
Thank
Okay.
you, Elena. All right. So I think that Elena and Jos and Giancarlo did a good job of covering a lot of the benefits of tubular ultrafilters and direct filtration applications. I'll get into a little bit of a case study on egg processing projects. A little bit about Dynatech. We've been providing.
Excuse me, Mike. Can you please make a full screen? Because you
Oh,
don't have it
sure.
in full
I thought I
screen
had.
mode.
Yeah.
Okay.
There we go. Thank you. Thank you. All right.
Thank you. Perfect now.
So yeah, Dynatech's been providing wastewater treatment systems for industrial customers since 1979. For about 35 years now, we've focused on membrane systems as part of the solution. We provide complete turnkey systems. In addition to the membranes, we'll use other treatment technologies, including chemical, physical, biological, and other technologies as well. This is a small sampling of the number of the different types of applications we've done. Over 1,000 installations, primarily across North America, hundreds of different applications, and many years of experience. We do all of our engineering and skid assembly and fabrication in-house. We do offer turnkey systems. We can offer installation for some projects. We have a number of projects where we have we call it D-boom basis, where we design, build, own, operate, and maintain these systems for our customers, and we do that on a cents per gallon basis to the customer. We provide maintenance support, and we also do treatability work in our lab at our office in New Jersey, and we also have a number of pilot systems available to do further investigation for potential projects. This is direct filtration is a simple process, and here's a simple illustration to show with the general concept of it. The ultrafilters that we use from Berghoff remove anything that's greater than 0.03 microns, so it removes all that is insoluble. It removes oil and grease. Does not remove dissolved inorganics or organics in solution, and it can concentrate with tubular UF. You can concentrate the contaminants to as high as up to 5% or even higher, depending on the nature of the solids that you're concentrating. The advantages of using tubular UF versus other types of UF or other types of filtration is that the ability to treat raw or just partially screen wastewater reduces the amount of upstream filtration, upstream screening or filtration before a UF. high solids are acceptable. It's more resistant to fouling than other types, and it enables greater product recovery. It can reduce the footprint needed. They can be put. There's flexibility in where they can put, allowing. So if it's not directly next to where an EQ or a receiving tank is, that can be acceptable for tubular UF. Produces high quality permeate, which reduces need for further downstream treatment, and it offers more water reuse opportunities. So often UF permeate is acceptable for reuse in some applications, and if further purification is needed, ultrafiltration provides the perfect feed quality for reverse osmosis. In egg processing applications, there's a high amount of solids, in addition to proteins, fats, and emulsified oils. It could be very high BOD, COD, and TSS. Other methods of treating egg processing wastewater is sometimes just dissolved air flotation alone, or DAF followed by biological treatment. And we'll talk about that a little bit later, but both of those are not very good for concentrating the solids as far as direct tubular UF can. And the UF also offers more opportunities for reuse than DAF alone. So here again, it's very simple. Using a tubular UF, it's very efficient at treating egg processing wastewater. The permeate is suitable for discharge. The concentrate that is generated in the process tank you're often able to dispose of that for no cost, because you can send it to a renderer who will treat it further. So it becomes a valuable product. You're generating it could be a potential additional revenue stream for the customer. Now, this is a specific project that we've completed, where it's the average flow is about 120,000 gallons per day. It is high strength. The BOD is near 7,000 milligrams per liter. The TKN is over 850, and the phosphorus is about 58 and a half. So this just shows you it is simple. There's process tanks. I mean, the core of it is a process tank. In this case, there's two process tanks, which we'll talk about in a few minutes, and an ultrafilter skid. And the sludge or concentrate that's pulled off of the process tank is sent to a renderer, which eliminates all sludge hauling and sludge disposal costs to this customer. And so here the goal was BOD, TKN, and phosphorus removal. Those were the three parameters that were important to this customer. And the UF alone, without any biological treatment, without any chemistry added, is very, very effective at reducing all three of those parameters. So first, for BOD, the average influent at this plant was almost 7,000. The average effluent was less than 5 milligrams per liter. So it was a 99.93% removal rate, which is pretty good. Same for TKN. The average removal rate was 99.88% with just filtration, no biological treatment, no chemistry added. It's just a very simple process that gets very good results. And phosphorus wasn't quite as good as the other two, but still pretty good at 97.86% removal, 1.28 milligrams per liter in the permeate from the UF. So all three of those, it was really, really effective. And it's a simple process. And so Here you can see side by side all three of those parameters: BOD, TKN, and phosphorus. And the key to this in this application is treating the wastewater rather quickly as it leaves the plant. So there's no equalization tanks. There's 2 process tanks. The process the way this would work is process tank number 1 would be used to feed the ultrafilter for a day. At the end of the day, or the next day, early the next day, the feed from the plant, or the plant effluent to the wastewater plant, would switch from tank number 1 to tank number 2. Tank number 1 would continue to be concentrated down using the ultrafiltration skid until a point where it reached its maximum concentration, and then it would be pumped to a concentrate holding tank that would then be emptied by the renderer. And then as tank number 1 when tank number 1 reaches its maximum concentration, the process tank number 2 would then be used to feed the ultrafiltration system, and it would switch back and forth on a daily basis like that, allowing you to concentrate as far as possible the waste while not letting it while treating it quickly. So we don't want to run the same tank for several days in a row, because some of those things will solubilize and will not be removed by the ultrafilter if we let it sit longer. So at the top, you'll see with this customer also had a DAF on site, and their average removal rates, you can see compared to the UF, were not nearly as good. The BOD, they were removing less than 2/3 of it. The TKN, they're removing less than half. And so they were with a DAF alone, they were not close to meeting their discharge limits of, in this case, of 300 for BOD, 32 for TKN, and 10 for phosphorus. Well, they're meeting the phosphorus limit, but they're not close on the others. They did also test a DAF followed by MBR, which also got them very good results, but it's a more expensive system, and more expensive to capital wise, and more expensive to operate because it's a more complex system. The DAF needs more attention than the UF, and with the MBR, you have additional equipment for the biological component of the system. So the simplest and most effective way to meet their discharge limits was just a UF. So this shows that the tubular membranes are well suited for applications like egg processing, where there's high solids. The permeate that is produced is consistently high quality. There's minimal chemical cost. There's no chemicals used at all in processing the wastewater. For the only chemicals used are for cleaning the membrane skids on occasion. And the automatic nature of the operation reduced operator attention significantly. And the waste that was generated, especially since no chemistry is added to condition the waste, makes it a valuable product that they can sell to renderers, perhaps generating income, or at the very least eliminating the cost of disposal. Here are just several examples of direct filtration, raw wastewater on the left versus permeate on the right. The one on the bottom right is from a food application with starch. The other ones are oily wastewater applications. But in any case, you can see that the oil and grease and solids are all removed. And that's all I have for the presentation. And I guess I'll turn it back to Elena.
Okay, thank you very much, Mike, for sharing your experience with us. Please, Mike, don't let us, and I will ask, let me share my screen first. I will ask Josh, Giancarlo, and Mike to rejoin for going for some discussion, okay? Okay. Well, we are now approaching the final part of the webinar, but I would like to discuss a couple of things with you, just for having your input on this. Well, during your presentations, you have mentioned, of course, piloting. I think it is something that can be quite important, especially when dealing with direct filtration projects, where each wastewater can be different, and you need to make some trials. So I would like to know from you which is your common approach regarding to this, which kind of guidelines or recommendations, and how to address a new project with direct filtration with the end user. Is piloting something that you are suggesting really frequently, or how do you normally manage this? Or do you rent a pilot, make a small lab scale trials? Which is your usual experience regarding to this?
Should I comment first on that?
Yes.
So yeah, of course, lab trials can be of value in an early stage of screening and validating a filtration process. In the situation that we are dealing with, or industrial applications, especially the example that I just highlighted, we tend to use, let's say, mobile pilot units, and used your type of membranes. Doesn't have to be an 8-inch or a 10-inch 4-meter module, but a 3-inch or even a bit smaller and shorter element will give us enough, let's say, capacity to run at an industrial site. Because for us, it's important to test variations that you would see in the industrial scale as well. So sending an IBC of 1,000 liter to our own pilot facilities is an option in an early stage. But if we expect, and if the customers knows that there is a variation to be expected in the feed composition, then you have to test it. In the case that I explained is quite extreme, there we tested even a couple of years in a row to test variations in crop yield. That's quite exceptional. But typically, we just finished a pilot with Berghoff membranes about a month ago, and there we tested, let's say, 4 weeks on site, and that was enough to test all the variation that you could expect in that type of application. So mobile units with a certain capacity gives us at least enough confidence to validate the process on.
Perfect. Understood. Giancarlo, something to add there, which is your normal approach, or how you manage this kind of things?
Yeah, I fully agree that here direct filtration requires a different mindset compared to the traditional MBR. MBR, the project development is more process on paper. Direct filtration is really case by case, and testing will be very, very important. The good news is that even small scale testing normally provides quite reliable data. I see most often we move to the customer location with a small test element, 1 meter long, and the data that you get out of that normally are quite representative of full-scale installation. We have seen scale up directly from the test element 2-inch 1 meter to quite big scale with good success in terms of matching the parameters, the permeability, cleaning procedures, and so on.
Okay, understood. Many thanks. Mike, would you like to add something here?
Yeah, I agree. I think that even small scale treatability work in our lab, like bench scale testing, can be very helpful to verify that direct filtration is the appropriate solution. And piloting, especially in novel applications, is very important. I think sometimes there are applications that we see where we've done repeatedly, have dozens of installations in similar applications, and in those cases, I think just having the appropriate data from the customer and perhaps doing bench scale treatability is sufficient to, and piloting might not be necessary in those projects.
Okay, thank you. Another thing that I would like to explore a bit is regarding the pre-treatment before the ultrafiltration. So, well, I would say that as in almost any membrane system, there is some pre-screening required, just in case there are big solids or big fibers that can, create some kind of clogging or problems with the tubular membranes. So, what do you think would be like for you the most standard pre-treatment before ultrafiltration? So, I don't know, is this rotary drum or this kind of basket strainers? What is common in your case?
So we often use basket strainers or automatic strainers, and you're right that even in applications where you don't think there will be large particles that you need to worry about, there often is. In the egg applications, for instance, the most recent one we've done, they've found coming to the wastewater treatment plant from the processing plant, they found utility knives, gloves, all kinds of shoelaces, all kinds of things coming out of the plant that need to be filtered out of before it gets to the ultrafilter. So yeah, you're right that some kind of screening in most applications is necessary.
Okay, understood. Giancarlo, yes.
I would add we should be careful with fibers, because normal self-cleaning filter and basket filters are maybe not so effective on fibers. And when there are fibers, I would rather consider gravity filters and better disc than rotary drum.
Okay, interesting. Josh, I don't know, in your case, maybe I was thinking more on wastewater treatment projects. In your case, maybe this is somehow different or
No,
it is
but
more or less.
I think the approach is similar to what has been said before. You need to consider that there might be a moment there where if you don't have pre-filtration or a screen or whatsoever is not in place, that you might have a risk in blocking the membranes in case some emergency comes up. In our case, if the product stands too long, or then there is even an opportunity that the coagulation of proteins happens earlier prior to UF, so then you might have blocking of membranes as well. So there's not a standard solution for that, I think, besides what has been said before. But it's for sure something to consider. And in the application that we did, we had an opportunity to leave any pre-filtration out of the design and still running successfully. But we have adjusted the design and the process of the specific UF in this case as well. But it's quite unique for that application, I would say, and that's not standard for every application.
Okay, thank you. I have here a question for Giancarlo related to CMP wastewater containing silica. Particles are hard. The question is if operating with a typical cross-flow velocity of 4 meters per second, in this case, can be can cause membrane damage, and if you would suggest maybe a slightly lower cross-flow velocity.
Yeah, correct. We have seen in case of hard silica particles that velocities in the 4 meters per second may be dangerous. And as permeability is anyway pretty high, so you may prefer to go to lower velocity in the 2, maximum 3 meter per second range, because you are getting anyway reasonable performance in terms of permeate production. And while lifetime is much improved.
Yeah, okay, understood. There is another question for you, Giancarlo. I don't know if I understand. For Giancarlo, if you could give us some recommendations to get a filterable water quality media. For examples, in cases where we have COD less than 20 ppm and silica 120 ppm. I don't know if I really understand the question.
Yeah, we should consider that it's really filtration. So any soluble organic will go through. And that's why I said that this type of application where you remove only particles are very interesting when the original water quality is pretty good. We have seen situations where there is pollution by additives or whatever. And in this case, you need to face different challenges. That is, you need to introduce chemical cleaning, typically, because organically solved matter will impact on the fouling of the membrane. And second, you need to consider that smaller soluble organic particles will go through, and so eventually for reuse, you would need also extra treatment like RO or oxidation or activated carbon or whatever.
Okay, understood. Mike, there is a question about the egg processing wastewater, and they would like to know which is the recovery that you are achieving in this kind of projects. If something like 80–90% recovery is something common. Do you have this information for the egg processing project?
Yeah, so yeah, I think 90% is a reasonable target. Perhaps you can go further. What restricts you from going further often is the fact that you don't want to treat it quickly, and so you don't have time to if you're able to keep adding to the same process tank and concentrating for a longer period of time, you could probably improve that recovery rate. But since you want to do it quickly and then concentrate it quickly, it limits you a little bit. But I still think that 90% is certainly achievable.
Okay, there is a question here in general, I think, is it a once-through process or recirculation process? Well, I would say that in any kind of tubular ultrafiltration system, you will always have this internal recirculation for creating the cross-flow velocity. And then, I would say that it depends. For example, if recovery is, let's say, 80%, what you can do is you directly feed 100, you have 80% as permeate, and 20% continuously discharge as the reject. On the other hand, I would say that when you really want to achieve high recoveries, it is more like a recirculation process. Giancarlo, there was also a question regarding the chemical cleaning for CMP wastewater containing silica, but well, you more or less already went through this?
Yeah, also because if on the contrary you want to impact the silica itself, then you want probably you need to use extreme chemical condition and membrane is not compatible. So I do not see CIP in case of particle removals as a strategy to impact on the main contaminant. It may impact only on the additives, if any are present.
Okay, okay. There is a question for direct filtration of digestate. Regarding the suspended solids concentration and permeability, these kind of things. I don't know, Giancarlo, maybe you can add something, but well, from my side, I would say that we need to deal always with the liquid digestate after liquid solid separation, and then in this sense we could be thinking on achieving suspended solids concentration of 30-35 grams per liter, and fluxes it depends a lot on the type of digestate and maximum suspended solids, but it can be something between 15, 20, 30 LMH. We have some experience up to 50 LMH in some specific cases, but yeah, permeability of digestate is quite low in general. It is a very challenging stream.
Yeah, it's challenging. It's colloidal. The viscosity is increasing fast with the solids concentration. So I would say up to 3%, okay, 3 to 4% range in terms of solid concentration. It's borderline, and more, in my opinion, it's becoming really difficult also because pumping system will probably need some very special option, not centrifugal, standard centrifugal pumps and so on. So I agree, I fully agree. You should stay on pretty low permeability, low flux for this design, and you need to consider that solid concentration will impact substantially on the flux.
Okay, thank you. There is a question related to, can these membranes be used in the oil and gas industry to remove oil from water? I think the answer is yes, you can use them for treating oily wastewater. I think that, Mike, you have quite a lot of experience in this kind of applications. I don't know whether it is oil and gas industry or automotive, but I think, yeah, you have some projects dealing with oil water separation.
Yeah, so we have hundreds of installations on oily wastewater. Not all of those are in oil and gas. Like you said, some of those are automotive, and a lot of other manufacturing applications. But we've done oil and gas applications. We've done refinery wastewater. We've done that with direct filtration and with MBR, and some really high oil and grease concentrations. So yes, these can certainly be used in those applications.
Could you? Yes.
I want to be nasty. In case of oil and gas industry, it's not that membrane is not applicable to produced water. Produced water could eventually be processed with membranes. Problem is that the oil and gas industry is not so willing to treat water.
Yeah.
Because for many reasons. I mean, it's obviously sometimes it's challenging environment like offshore, but even onshore is not so easy.
Okay. Does any of you have like a maximum limit of oil content in the wastewater? And what will be reduced ppm? Well, in terms of permeate quality, membranes will remove all the emulsified oil. So you can expect less than 5 ppm of oil in the permeate. A maximum limit in the influent? Well, I don't know. We have references, I think, running up to even 100 grams per liter of oil in the reject. It is a question also of selecting the flux for design. But I don't know, Mike, do you have some figures in mind for maximum oil and grease?
So no, that's a good question. So for for the Berghoff membranes that we use, I don't know. I agree with you that it can be fairly high. I don't know. I couldn't give you an exact number, but I know that for some applications, what we've done is used Berghoff for we've done a two-stage ultrafiltration system. If concentrating that oil and grease is really important to concentrate it as far as possible, we've done a two-stage system where Berghoff is the primary stage, and then we have a smaller ultrafilter that's capable of achieving a higher concentrations, treating the concentrate from Berghoff. We've not done that a lot, but we've done that several times where they can create a valuable product out of the concentrate, and so that the high concentration is important in those situations.
Okay, thank you. Well, I think we are running out of time. Giancarlo, did you want to add something here, or Josh?
No, eventually, about oil. Consider that if it is a good emulsion, good quality emulsion, you may operate with high oil concentration, 3%, 4%, while if it is free mineral oil, even 100 ppm is a lot. So it's very difficult to give a number.
Yeah, understood. Okay. Well, so now if you do not want to add anything more, I will go to just the last slide. So well, this brings us to the end of today's webinar. Probably some of the questions that you were including in the chat, well, we didn't have time enough to go through all of them, but in any case, we will review them, and we can even contact you directly with the answer for these questions. Once again, a big thank you, to all of you, all the attendees, but especially the presenters, Josh, Giancarlo, and Mike, for many thanks for your excellent presentations and the information, and for sharing your know-how in the end. Before we end up, just a quick reminder, you can see our contact details on the screen. So please feel free to reach out if you need further technical information or have additional questions, or if you want to have information about references or case studies, or you have any potential project that you would like to discuss. And of course, if you are interested on renting a pilot plant or similar for validate or demonstrate the technology. So you have all our contact details there. So having said this, thank you again for joining us today. We look forward to staying in touch, and we hope to see you at future events. So from my side, just telling that please enjoy the rest of your day. Goodbye for now, and many thanks. Thank you.
Thank you.
Thank you.
Thank you. Bye-bye, Josh, Mike, Giancarlo, many thanks. Bye-bye.
Thank you. Bye.
Ya he visto.